Recording is in progress. Take it away, Larry.
All righty. Well, good evening, folks. As Dan said, my name's Larry, K4LDC, and I got drafted to give a little presentation about solar weather, mainly the numbers that we see every day or however often you look on QRZ or at the bottom of the SCARS website. So I just wanted to kind of tell you the numbers that I focus in on and kind of what's important to us, how it affects our specific HF operations. So just to start off with, can everybody see my screen okay?
Yep.
Let me go in here and increase the mouse size real quick. If I can get to that button. Where's that at? There it is. Just so. Okay. Okay, anyway. Okay, back to the.
That's better.
Yeah. So solar weather is basically all these events happening on the sun, spewing particles towards the earth, and then we have our magnetic, or the magnetosphere, which protects us from a lot of this, but it also affects, you know, auroras, ionosphere, geomagnetic storms and stuff, which impacts our HF radio operations. So it's kind of a double-edged sword. We need it in order to have good HF operations, but you know, like all things where you have too much of a good thing, too much of a good thing becomes a bad thing in the HF radio world. So it's a balancing act. And so we look at a lot of different data, and NOAA spits out these numbers every day. And let me pull up this chart here. I'm just going to drag this up to my desktop. Can everybody see this one okay?
Yep.
Yep, we see it.
All right. So up the top here, you notice this is the data from the SCARS, bottom of the SCARS webpage. And this is courtesy of N0NBH. And he's put all the solar data into kind of a easy to read and somewhat intuitive table, I guess you could say. So we can get a quick glimpse of what to expect in the HF radio world. And there were some questions about, you know, what do all of these numbers mean over here? And I'm going to go through, you know, each line here and kind of tell you what impact it has to the HF, to our HF band operations. But the really easy way to look at it is just jump over here to HF conditions, and he has decoded all of this and turned it in, and it tells you basically what all these numbers, what they represent as far as our HF conditions. And you'll see how it lines up here as we go along. So let's see. And I'm going to focus in on probably the two most important lines, which is going to be the solar flux index and sunspot numbers and the X-ray. And you'll see why here in just a minute here. Okay, so I'm going to define, this is kind of a definition of what those numbers are and what impact it has to our HF operations. So you got your solar flux index and the sunspot number, that's on that first line. And those affect the F layer ionization, which is what, you know, we need in order to bounce our signals off of the F layers and make long distance DX operations or contacts. The next one is the A and K planetary index. And this gives us an indication of the geomagnetic stability, which is responsible for a lot of the signal fading that we hear. You know, you may be on the band and you'll hear the signal kind of come up and go down, or, you know, sometimes it'll go all the way and just disappear and then come back. This has a lot to do with that. If there's a geomagnetic storm going on, because you get those pulses coming in and they basically just wipe out your signal. I think the next line down was the X-rays, and this is an indication, or it impacts our D layer. And you know what we know about the D layer is it absorbs your HF signal, and you'll see in a minute why that's important to understand what's going on there. And then the 304A angstroms contributes to the ionization of the F layer. So the higher number there is a good thing because it helps stabilize that F layer ionization. Proton flux typically impacts the E layer, which is for helps us with 10 meters, 6 meters, whatnot in that area. Yeah, but it also impacts polar regions as far as HF radio blackouts. And electron flux, pretty much the same thing as proton flux. So like I said, I was going to talk about why the D and the F layers are important to us. Basically, you got the F layer, we got to get that ionized so we can get our signal to bounce off of that and make our DX contact. But if we get too much radiation from the X-ray, it starts activating this D layer, which is on the sunlit side of the Earth only, because of the constant, bombardment from the sun. It attenuates your signal. So as your signal comes out, it might be S9 coming up here, goes through the D layer, it cuts it back some. Your signal bounce off the F layer, comes back down through the D layer again. It's going to get attenuated some more. You might end up with like a S3 over here. So high solar flare and D layer absorption is not our friend, but high F layer is. So it's kind of a double-edged sword. So this is kind of the basics of our DX operation, what's impacting it. Let's see, we got that done. So earlier in the week, I'd sent out a copy of this PDF here, and this is basically the decoder ring for that chart from N0NBH, which we've seen at the beginning. And what I've done is I've highlighted the columns that relate to the D and the F layer, because that's the most important to us, really. And if you look back at, let me see if I can go, I'll pull up a screenshot here. So if we go and look at X-ray down here, you can look over here at the number that I got highlighted, and that'll tell you basically what that means as far as the impact to our HF operations. Right now it says, or well, this one says B 2.6, which is down at the bottom of that table. Let me see if I can pull the table up here. Let me do it this way, a lot easier. Can you see that okay? Everybody see that okay?
Yep, we see.
No.
So if you look, let me scroll down here. Okay, down here at the bottom, low numbers are good. Bad numbers or high numbers up here are bad, with the exception of the sunspot numbers. High sunspot numbers can open up the bands for you. But if you go down here, B216 for the X-ray, that's down in this range, which is, basically normal HF, no HF, impacts to your HF operations. So the X-ray is your D layer, and then the solar flux index, which is this top number, and a sunspot number match these over here. So I highlighted the sunspot number, but the first number over here is your solar flux index. And they're pretty closely correlated, so that's why they grouped them together. So if you look at that, it says 38. You go down here and you see that, sunspot numbers in 38, fair band conditions up through 15 meters. And remember earlier I said that, he's decoded all these for you. Well, if you go over here and look, up through 15 meters is good and even is, fair or good. So he's already kind of decoded that for you right here. Yeah, let's see what else we got here. Okay. Yeah, go back to the other one. I know it's back there. There it is. Oop, no, not it. I got too many screens going here. All right.
Is this solar information the stuff that's available through the ARRL?
It is, but it doesn't really decode it, I don't think, as well. I mean,
Okay.
The numbers are there. I'm kind of a visual learner, so if I can look at everything in one little snapshot, I'm a lot better off than sitting there reading through a bunch of numbers. There we go. Okay, so anyway, what else? Okay, the planetary A and K numbers right here, 6 and 2. The K2, if you look over here, lines up with their geomagnetic storm number. And you can go down through here and see what that equates to. K2, 0 to 2 is what that range. It's inactive, quiet, no impact to the HF. And auroras are going to be 67 to 62 degrees latitude. It also gives you a noise level, and this is kind of something to keep in mind. Remember earlier when we looked at the D layer, go back to that chart, your signal's getting attenuated. Well, if you get down to, say you're an S3 here, and for some reason, let me get back over this, say this K2 number is actually up higher, say it's like K5, well, the noise level S4 to S6, chances are they're not going to hear you. Because if your signal's been degraded to S3, going up and back through the D layer, by the time it gets to the ground, and the noise level is an S, 4 to 6, you're gonna make that contact. So that's, you want to kind of keep an eye on that. It's important as far as the geomagnetic storms go to see what's happening there. And he has decoded that for you over here as well. Geomagnetic field says quiet. And if you go down here and look, that's sort of inactive, quiet. And if it's in this range, it'll say unsettled, active, and on up. And also, earlier I said the geomagnetic storms can cause signal fading. So thing to keep in mind is these numbers are kind of like an average prediction for the day. So it may come and go. And if you got a geomagnetic storm coming, you can expect the signals to be fading in and out during that time period. And let's see, let me go back to this chart here.
Hey, Larry,
Yes, sir.
where did you say this little chart that you have up in the left-hand side? You said, how can you see that chart, that particular chart where he has decoded that?
That is, you're talking about the one You talking
Yeah,
about
the
this
one
one?
you can see here, that's kind of the narrow band on the picture here. How do you see that picture? How can we see it?
It's
So
on the bottom of the SCARS website.
Oh, okay, all right,
And also the same information is on the homepage for QRZ.
okay,
So the homepage for QRZ, it's in a different format, but it shows the exact same data. It's just stacked a little different.
okay,
And if you use this chart here that I sent out earlier, and I'll post this on the in the file section on the groups IO as well. You can use this as a quick indication that, hey, I need to look at X-rays for the D layer, and I need to look at solar flux and sunspot, for my F layer to see if the band's going to even be open. And then the 304A, the electron flux and the proton flux, or these columns here, you use proton flux for the solar radiation storm, and it'll tell you one impact based on the level of that storm. Same with electron alerts, pretty much the same thing. And those impact the polar regions. And I'll show you an example of that here, of those two impacting the radio communications here in a second. Okay, where are we at here? So, and also in the email I sent out earlier, I had mentioned the NOAA radio communications dashboard, which is a website that NOAA has with all this data on it. And they've done a really good job of piecing together the information that's kind of peculiar to radio communications, so you don't have to go hunt it down. And they put it into a nice graphical display, which kind of gives you a perspective of what's happening. And I'll pull that website up in a minute and kind of go through it and give you a little bit more detail. And then you can go and play with it and see what's happening. And one of the other dashboard, or not dashboards, but this radio communication dashboard kind of focuses in on the D region absorption predictions, but it also gives you the solar storms, geomagnetic storms, and the X-ray, which would be your radio D layer blackouts. And it gives you the 24-hour observed, latest observed, and also gives you a prediction, which I'll show in a minute. And if you click on each of these squares up here, it gives you this little drop-down box that explains what it is. So if they say there's an R1, you can see that it's weak or minor degradation of the HF radio on the sunlit side of the Earth. So it's kind of a handy little tool to keep a shortcut to on your desktop. And then down here, it gives you kind of a graphical representation of the sunlit side at that particular time, and the level of absorption to expect. And over here is a graph of this data, and I'll explain that a little bit more here in a minute. And then here again is a history of the X-ray, X-ray flares, which that's impacting your D region. Polar proton flux, or the proton flux, which is affecting your polar regions. And then the geomagnetic storms, we talked about causing signal fade and whatnot. So this is a snapshot of that chart in 2012 that I took. I knew that day that we were having radio issues as far as HF radio. And you can probably see why from here. there was some pretty active X-rays and proton fluxes going on. So you can see, this again is the sunlit side it's showing. And there was a pretty good X-ray flux coming in, as well as proton flux, which is this area up here at the bottom and the top is the polar regions. So they were experiencing radio blackouts as well. If you go over here and look at this bar graph, it says attenuation and maximum absorption. Across the bottom is the dB readings, and then this scale on the left side is your megahertz. So down here at 3 megahertz, absorption was 35 dBs or greater. You're not going to talk on the HF radio with that happening, at least not through the F layer. You might talk to the guy down the street, but you're not going to talk on any DX when something like that's going on. And see, even down to 15 megahertz, or we'll say about 14, we still had 15 plus dB of attenuation going on. So not a good day for HF propagation there. The neat thing about that chart is, it tells you a approximate time that this is expected to happen. It's kind of a little movie that's I think it's a 2-day prediction, but gives you the time, but it also tells you down here in this blue area, your expected recovery time. So for the mid low level, which is the X-ray and the D layer, they're saying that's going to last about 52 minutes. And up in the polar regions, though, with the proton flux, that's going to last 23 hours and 11 minutes. So, if you're up in the North Pole, or say you're flying over the North Pole or South Pole, don't use your HF radio. It's not going to do you any good. Okay, let's see. So that's kind of an overview of the D-layered data. The other thing I was going to highlight was the ionosphere. This is a 2-day forecast, and this is impacting your F layer basically. It's a 2-day forecast that they got on the NOAA weather site website. And it kind of gives you a graphical representation of what is happening to the ionosphere. I think it says 400 meters or something. It's way up there, where the F layer is. But it tells you, this tells you the electron content. And I can tell you from looking at this, this is probably the daylit area right through here, because that's where it's going to charge the most up. Over here, this one is what they call the maximum usable frequency. It's a calculated number based on what is happening with the ionosphere. And if you look over here on the right, it tells you the megahertz, the higher up in frequency that the ionosphere will reflect your signal, the brighter the color is. So, right through here, you can probably talk, maybe even 6 meters DX, and out through here where it's real bright. And the one thing I noticed about this is a movie that'll play, and it'll give you the 2-hour forecast of what they think it's going to do as the Earth rotates and the sun shines on the daylit side of the Earth. An odd thing I noticed was it always, on the daylit side, there's always this trailing little bit left. And like over here, you can see the electron charging of the ionosphere is pretty intense. But right through here was the gray line. And you got these 2 little trails that's kind of trailing off, which theoretically would mean you could talk maybe some DX on the upper bands in this area during the night, which is typically not the norm for HF. So, and we'll play that video here in a second and show you what's happened there. So anyway, okay, so that's the end of the slides. So let me pull up that web page and show you what NOAA has, what our taxpayer dollars do with NOAA. Okay, this is, let's see, this current. Yeah, wow, okay. Can everybody see that all right?
Yep,
Okay.
I see it.
Let's see, if I go full screen, is it still there?
That's better. Yep.
Okay.
That's better.
All right. So this is the radio under their dashboard. This is a radio communication dashboard. And earlier I was talking about these scales here. They send out notices, and theirs will be like they're expecting an R1 or an R2 or something like that. And I think Tom had sent out an email earlier last week that listed all those. But that email, I mean, that link is actually right here under the NOAA scales. It'll tell you what these are. But if you click on this, you get a little drop down and it tells you, you know, no R scale, no radio blackouts, basically. So that's typically your X-ray, which would be your D layer stuff. Here we got solar radiation, and it's normal, so no storms there, and that would be your proton and flux, which would be your polar regions. And then geomagnetic storms right now, nothing. But and this is last 24 hours. The latest observed is these 3 blocks. And if you go over here, this is predicted for tomorrow. So tomorrow they're predicting a G2 for geomagnetic storm. So if you drop that down, it gives you a explanation of what that is. And that's, so let's see here. Power systems, high latitude power systems may experience voltage alarms. Space operations, you know, that affect spacecraft charging and drag in orbit, I guess. But we're looking at HF radio propagation can fade at high latitudes, and Aurora has been seen at as New York or Idaho. So that's kind of a neat tool to look and say, okay, I can expect maybe some HF propagation issues in the higher latitudes, which, you know, we kind of are in the higher latitudes. If you click the little arrow again, now you get the prediction for the 3rd, and the G2 is faded to a G1, it looks like, which really doesn't affect a whole lot. It affects migratory animals, though. That's interesting. So that's kind of a neat, quick way to look at, you know, all that data is decoded for us. Down here on the D region absorption prediction map, you can see right now that, you know, we're getting into the dark side of the sunlit sides over here, and over here, this would be the gray line running around through here. And the colors, if you look down here, kind of tell you the frequencies that are affected above 1 dB absorption. So it's kind of a light blue, so maybe up to 10 megahertz. And if you look over here, yeah, it's not a whole lot happening. Maybe 3 megahertz, probably 5 dB degradation could be expected on the sunlit side of the Earth. But other than that, everything's normal. No data down here to look at. Over here gives you a, let's see if I pull it up. Yeah, it's bigger. The history of what's happened in the last 2 days. And as you can see, everything's been pretty quiet. Getting close to an R1 for the flares, but everything else is pretty quiet. Okay, how do I get back out of that? Nope, that didn't work. Oh, there we go. The other thing you can look at on this page is the Aurora. And the reason this is kind of important, at least for me, is if I want to talk to China, my signal's got to go across the North Pole. Well, if there's a very active Aurora going on, that's going to attenuate my signal going across there. This is just an indication of the probability of an Aurora. So right now it's pretty low, maybe 10%. Click the little button, you'll see, is that showing up playing on y'all's screen?
Yes.
Yes.
It is.
Okay, yeah, you should see, you know, as the sun, well, as we rotate in the sunlight, you can see how that would affect signals going across the North Pole. So I'm going to stop this and move it around real quick here. So probably right there, if I wanted to talk to China, would be my best bet. And if you look up here, it'll tell me what time, about 22:55 Z would have been the best time to try that. Of course, that was a little while ago. But now, as we go around, you can see where possibility of an Aurora or something would cut off my signal. So kind of interesting information to know if you're going to send your signal up to the north across there to China. And this one is just an image of the sun that's showing you, the sunspots, and these two gaping holes here are probably geomagnetic storms headed directly toward us. And let me play that for it doesn't move very quick because the sun doesn't rotate real fast. So not much there. Let me go back to this one. Let's see if I do that. There we go. And we'll play that. Now you can see here as we rotate in and out of the sunlight, how the D layer moves along with that. Because remember, the D layer is only active in the sunlit area. It goes away at nighttime, so you don't have to worry about that absorption of your signal. Let me speed this up a little bit. So anyway, about 2200, I think it was. Right there. I got an email alert from NOAA of let me see if I can pull it up here. I thought it was kind of an interesting email. Oops, let me do it while I got this open. No, they won't let me pull it up. Okay. Anyway.
Larry, is that the purple area is kind of the gray line, isn't it?
Well,
is the gray line in that purple area?
Yeah, it's kind of in the purple area. It's actually right on the edge of the purple and the black.
Okay, thank you.
But that, you're right. I mean, that's getting close to the gray, excuse me, getting close to the gray line. And that kind of, that kind of represents, the sun is hitting us the hardest right here. So that's where your D layer is going to be the most active. And then it kind of fades out and then it goes away. So it kind of shows that it's a good indication of that.
So what was the email? You guys can't.
Well, I can't pull it up on that screen. That's weird that I can't put it on the other screen. But basically, it said geomagnetic sudden impulse. I'm like, what?
Sounds like a movie.
Yeah, and I thought, okay, what does that mean? And so I had to go look it up. But what that's telling us is to expect a geomagnetic storm. Well, guess what? They had predicted one tomorrow, sometime tomorrow, G2, geomagnetic storm. So that the definition of that email was actually this could be a precursor to a geomagnetic storm. So good call on their part.
Have you ever Have you used spaceweather.com?
Yeah, I've gone to their website, you know, and they got a lot of information on there.
Yeah, I was just looking at it, and I was going to ask you about this. It says right now a CME has arrived. A CME hit Earth's magnetic field on February 1st at 2221 UT, which is exactly where you are over here.
Yeah. And that's gonna, you know, it's gonna disrupt that, you know, that big bubble of geomagnetic field around us. So that's what's creating our geomagnetic storm. And, you know, too much, it's like a balloon, you know, you can push on the balloon and it kind of gives and then it comes back out.
Right.
Well, too much pressure and something bad can happen. And anyway, that's going to create that geomagnetic storm, you know, and if it's a really bad one, then of course you get a Carrington event, and that's not good. Let's see what. Trying to think here was something else I was gonna. Oh, okay. The other thing was the F layer, and that was this here. This one, remember I was talking about, okay, it's already changed from the last time I pulled it up. This was the sunlit side right here. You can kind of see, this is the D layer, the gray line runs around through here. So the sunlit side, this is another anomaly I've always noticed on this. There's always a dip right here. And I remember reading something about the magnetic field. There's some magnetic field anomalies through here because I think the North Pole tends to wander around up here somewhere, magnetic North Pole, which causes this right here. And let me play the video. It's kind of interesting. But you can see there's always a little, it's like everything has to make a little dip right through there because of the magnetic field. But again,
Larry, this is Dave. One thing you might note is there's a difference in variation, your magnetic compass variation on the east coast of the U.S.
Yeah.
Like where we are now is about 4 degrees east. When you get over around Alaska, it's like 20 degrees west.
Yeah.
So it moves considerably.
Yeah.
As you move further west.
And
that's
that's
probably what this is.
Yes, I was going to say that's probably part of this effect here, but it's always like that. And you know, I remember reading something in the aviation books about that. Anyway, but again,
your pilots will have a chart that as they go west, it will tell them the correction factor that they have to use with their magnetic compass.
Right, that's correct. Yeah, we had to update those charts every so often. I can tell you some wild stories about that. You gotta do a compass swing on an airplane. But before you do the compass swing, the place you do the compass swing at has to be surveyed. It's just a big, long process.
Yeah, I've done that compass swing on our airplane before. We used to do that on a
yeah. You know, Charles, that just about no airport anymore has a certified compass swing spot. You know, it used to have that marked out on a ramp somewhere. Nobody does that anymore.
Yeah, we used to have them in Germany there on the airbase where we bring the plane out of periodic or 50-hour inspection, and they'd have us taxi over and check it.
Yeah. They did away with the marking the ramp where you line the airplane up to do that.
I wouldn't have any idea how to do it today. Yeah,
they use instruments now to do it.
Well, they're all electronic flux gate compasses now, as opposed to hard compasses.
Yeah, but we still have a hard compass backup in the airplane.
Yeah,
and you still have to have that chart in there just in case. But
Larry.
Yeah.
Question.
Yeah.
If it's July for us, is that bubble, the bright yellow bubble that hangs down toward Antarctica, is it going to be inverted?
It's further up here. Yep.
And will it still have that dip on top of it?
It'll have a dip up here.
All right.
Yes, it's just, I noticed that, you know, looking at this data all the time, I just noticed that as we went along. But anyway, so anyway, this is, you know, right here is where the sun is hitting the most, energizing that ionosphere. And then of course, you know, we was talking about this earlier. You can see there's two little trails that kind of linger out there into the dark area, which could be good for DX. And again, over here, this chart is basically taking that data and converting it into what they think the usable frequency will be for skipping off of the ionosphere. And let me go back to it. So you can see as that goes across, you know, as we rotate and the sunlight comes and goes, how that fluctuates going across there. It also gives you an idea of how unstable that area is too. You know, you look over here and it looks, well, that's pretty solid, but over here, when you look at what the usable frequency is, you got, you know, areas that it's real intense and areas that it's not real intense. So.
Larry, there's one other thing I would add to that. If you notice those two lines are just above and below the equator, they also happen to be just about where the trade winds are.
Yeah.
Almost exactly where the trade winds flow.
Yeah.
So,
yeah.
And I've always wondered if that's part of how the trade winds work, is the difference in the magnetic field there.
Yeah. Well, yeah, I mean, you know, the sun heating that up affects our weather here on Earth just as it does up there. So I'm sure it is. And this is kind of this gap here is kind of centered on what would be the center of the sunlight shining. You know, in the summertime, it'll the deal too of, you know, why certain times of the year we can talk, you know, on 50 meters over to Europe, and other times we can't. The ionosphere is just not favorable in that direction. So it's kind of a neat tool to look at. And
hey Larry, I'm sorry if you already said this, but what's the difference between the I mean, I know what maximum usable frequency is, but the Muff versus the Muff anomaly. What's the Muff anomaly?
Oh, this down here, the anomaly is they've taken this data and compared it to the last 10 days worth of data, I think it is. So they're looking to see if there's any drastic changes, I guess is what a good way to look at it. I don't really, because it's looking at historical data, I don't really care too much about it. But you know, you can kind of see that it's pretty much mirroring what's up there already.
Okay, thank you.
Except for, you know, here you got a little, what appears to be a kind of a dark hole that's up here too.
The graph on the scale on the right side of that.
This scale here,
like a is that showing is that showing like a deviation from?
Well, this is just showing
frequency.
The megahertz. This is just showing what oh, that might be, I don't know.
Is red.
Yeah.
If it's the high end of red, they're like 25 megahertz off.
Could be, yeah.
In a high red area. I don't know, making that up.
That would make sense since they got positive and negative numbers there.
Kind of like a deviation from.
Yeah. Yeah, I really don't worry too much about it. I want to know what's happening now.
Yeah.
You know, but this does give you a 2-day forecast. So let's see, where are we at here? Yeah, so this is out to 1800 on the 3rd. And again, it's the forecast, so take it for what it's worth. But kind of a good tool to look at if, for contest weekend.
Larry, have you ever run a check of this information against the log 4OM propagation program?
Well, now, a lot of that data is this data, just in a different format.
Oh yeah, well, it's supposed to pull it off of these websites. That's where it's pulling it from.
Yeah, it all comes from NOAA.
Yeah, it makes it real quick.
I haven't looked at the log 4M.
I mean, it's pretty accurate. It really is.
Well, it should be if it's using NOAA's data.
It
And
puts
it's
your
just
data
like
out there.
vocap, you can go into vocap and calculate.
Yeah, I
point
mean,
to
that's what I use it for propagation, because it's really
Yeah.
quick.
Yeah,
It shows you, and also you can set it for any frequency you want and run a propagation forecast on it. And boy, it spits it out for you in about 15 seconds.
yeah. And this is just kind of the density or activity that's going on. Same, pretty much same, only I think it's kind of like this, but it's just not as pretty. So anyway, but the NOAA website, I think, is pretty good if we're looking this information up. Another thing I'll point out, this subscribe right here. You can go here and subscribe and get the email alerts, kind of like the one I just got. And this tells you what those are. And you can go in and select, maybe you only want the most severe ones or whatever, so you don't get overloaded with a bunch of spam email. Like get an X-ray flux of an M5. Well, you're not going to be talking on HF radios for tens of minutes, it says. But this is a kind of a good tool also for your toolbox. So it emails you ahead of time, let you know what's happening. These dashboards they have set up for different disciplines have different information on it. Some of it's a duplicate of what's on the radio one, some of it's not. But the one that has everything is a space weather enthusiast. And it's got, it's got the numbers, it's got the charts, it's got the sun, solar disk. This one, you can see the flares coming off of the sun. Solar wind predictions. Auroras again, D-layer, all that. But down here at the bottom, this is kind of a one to keep in mind, is this is the sun cycle progression and the reported numbers. So you can see where we are at in cycle number 25. So you can also go back and look at the other cycles way back and how high they were. And let's see. So they're predicting a value of 115.3 in July 2025. Not a very active cycle. Of course, trending a little bit up from that right now, so maybe it'll get better. Anyway, that I won't bore you with any more of this, but
so can we put these URLs on?
I will put the
place on the website.
Yeah, in fact, what I'll do is I'll send it, or I'll post that the slides.
Yeah.
These slides.
Yeah.
Because I got the links are right here. You click on them and it'll take you to.
That works.
To that, but you can also, once you get there, you can look at the header. It's kind of self-explanatory.
Yeah.
But in summary, that's basically the impacts of those elements coming from the sun and what they do to our HF band, and what to look for. The main thing is the F and D layer, because that's the ones that's going to impact our DX operations the most. The geomagnetic storms are going to affect your signal fading. That if you don't have this up here, it doesn't matter. And if you have too much of this, it doesn't matter. So it's a balancing act for those two to be in sync where you can get through. That's the magic of space weather.
Awesome. Anybody
All
else
the
have
numbers.
questions?
Any questions?
Yeah, you gonna have links for this and later the meeting. Tom had surgery procedure today and he didn't feel like sitting, but he'd like to watch your presentation at a later time.
I have recorded this to my computer. We'll figure out where to put it. Probably upload it to YouTube
Okay.
and get it out. So I need to see it about 15 more times.
Yeah.
And think about this. I want to try to coerce Larry into doing a forecast next big contest weekend. Maybe we could do a
I
quick
can't give
call.
away my secrets.
Okay, never mind.
No.
But I'm thinking it might be good. I know it would help me if maybe we got something big coming up, if we could throw together a quick session and let you kind of walk through what you look at on this.
See what we might expect.
You know, having this kind of information at field day would be good too.
Exactly.
Oh,
Yeah.
Exactly. That's what I was thinking about. Exactly.
Yeah.
I'll tell you,
Okay.
There's lots this weekend. You need all the help you can get. So what it is this weekend.
this past contest, Sunday, when I turned on the radio, I noticed there was more static than there was Saturday. And, I went and looked at this data, and sure enough, that geomagnetic level was up a little bit, which increased the static noise level. Wasn't enough to, cut down on the contest.
Well, after the contest was over, I went on the SDR and looked, and 10 meters came in. We could have used it Saturday.
Yeah.
Dead.
Yeah. And that's why I said it's a double-edged sword. That you need some activity in order to get everything working. And you need a lot, but then you get a little bit too much and you're all over, you're done with.
Kind of like snow in Georgia. It's got to be exactly the right setup. And it's
the right temperature so it doesn't stick to the road.
That's right. That's right. That's right.
Hey, Larry, I'm curious. You know how it's given like the S level. Is that a good reference for like where the S levels should be on my meter?
No, I forgot to mention that. That's not gonna, if you're in an area where you got like S5 all the time, that's local static noise. It's not gonna, it doesn't have anything to do with that. This is like if you're out away from everything, clear air, no electronic noise around, this is what you could expect it to be.
If you got high noise level also, it could be stuff in your local area or right in your house causing part of that.
Yeah, that's what, yeah. Like say your static S level is S5, that's locally produced noise there.
Mm-hmm.
So you really won't, let me pull that back up. You really won't, it won't make an impact till you get up here probably around K6 or K7 before you start noticing that, somebody that has a real low noise level will notice it down here on weak signal, that up here is where you're going to start to notice it on your weak signals. But, your signal's already hampered by the local noise level. That makes sense?
It does. It does. Thanks. It's sort of like I guess like a theoretical S level, sort of like what is it, the isotropic dipolar.
Yeah, that's a good.
I think it was Rick Bohall one time found that he had a high noise level on his radio, and it turned out to be a one of these wall warts, if I
Yeah.
recall correctly, that was causing a majority of his problem. And it was in his, I think it was in his camper.
Yeah, wall warts are,
You had a good presentation tonight. That was good.
Yep. Thanks
I'm
very
like
much.
Jim, I'd like to listen to it a few more times to kind of understand everything.
yeah, hopefully, it was informative. The big thing